Hi everyone. So today we're going to go through the oxyhemoglobin dissociation curve and the Bohr shift. And both AQA and OCR ask about this in equal measure. Roughly, it'll be about 3 to 4 marks. So it is important that you understand it, and it can be quite a tricky topic just given the amount of jargon in it. So firstly, let's talk about what is meant by these terms. So, oxyhemoglobin is just a fancy term for oxygen bound to hemoglobin. And per hemoglobin molecule, each hemoglobin can carry a maximum of 4 oxygen molecules. So, we're going to talk about hemoglobin saturation in a bit, its percentage saturation. And if hemoglobin is 100% saturated with oxygen, it will look like that. Each hemoglobin molecule will look like that. It'll have all 4 oxygens bound to it. Whereas if, let's say, another hemoglobin molecule here, if hemoglobin is only 50% saturated with oxygen, it would look like that. It would only have 2 out of the possible 4 oxygens bound to it. And what that means is with the other 2, it's let go of them. And instead of saying let go, they want you to use the word dissociate. So if you dissociate from someone, you distance yourself from them. So if hemoglobin dissociates with oxygen, it's letting go of that oxygen. And what this whole topic is looking at is when is hemoglobin more likely to dissociate from oxygen? And when is it more likely not to do that? When is it more likely to associate with oxygen? And when is it more likely to dissociate with oxygen? And that's what the Bohr shift is showing. So this is what the oxyhemoglobin dissociation curve looks like. And also I've drawn on the Bohr shift line in red. So the Bohr shift is when this oxyhemoglobin dissociation curve shifts to the right. And we're going to explain what that shift to the right demonstrates today. So firstly, let's break all the terms down in this graph so you understand what they mean. So as we've already just mentioned, oxyhemoglobin is just a fancy term for oxygen being bound to hemoglobin. And then dissociation means when oxygen is being let go from hemoglobin. When hemoglobin dissociates with oxygen, it lets it go. And on this y-axis, we've got the percentage saturation of hemoglobin with oxygen. And that is just a fancy way of saying how much oxygen is bound to hemoglobin. And I always think it's worth just thinking about this y-axis in regards to one hemoglobin. So if hemoglobin is 100% saturated with oxygen, one hemoglobin would have all 4 oxygens bound to it. If hemoglobin is 75% saturated with oxygen, the hemoglobin molecule will look like this. It'll have 3 out of the 4 oxygens bound to it, and that means that it's dissociated with 1 out of the 4. If hemoglobin is 25% saturated with oxygen, it will look like this. So it'll only have 1 out of the possible 4 oxygens bound to it, and that means it's dissociated with 3 out of the 4. So that's what the y-axis is showing us, just how much oxygen is bound to hemoglobin and how much oxygen has been let go from hemoglobin. And then on the x-axis, you've got the partial pressure of oxygen, and that's just a fancy way of saying how much oxygen is there somewhere. So if there's a high partial pressure of oxygen, it just means there's loads of oxygen there. If there's a lower partial pressure of oxygen, there's not as much oxygen there. You don't need to know these values off by heart, but this is just for a bit of reference. 100 millimeters of mercury is a lot. 40 millimeters of mercury of oxygen isn't a lot. And millimeters of mercury, you don't really need to understand that. It's just a unit of measurement. The same way that you measure the amount of a liquid in liters, you measure the amount of gas in a mixture of gases in millimeters of mercury, but it's not important that you know that. So in the body, there's always going to be a really high partial pressure of oxygen in the lungs. So we'll associate that part of the graph with the lungs. And then in the body, there's always going to be a low partial pressure of oxygen at the muscles, because the muscles are constantly using that oxygen up in aerobic respiration. So we'll associate that part of the x-axis with the muscles. And initially, what this graph is showing us is that when there's loads of oxygen somewhere, hemoglobin is fully saturated with oxygen. So at the lungs, every hemoglobin molecule will roughly look like this. It'll have all 4 oxygen molecules bound to it. And that's just because at the lungs, there's loads of oxygen available. So that oxygen is just going to come and bind with hemoglobin. So there's loads of association going on at the lungs between oxygen and hemoglobin, loads of oxygen and hemoglobin binding together. Whereas if we go to somewhere like the muscles, where there isn't as much oxygen available, and we work up to the line, it's telling us that instead of hemoglobin being 100% saturated with oxygen, it's only 75% saturated with oxygen. So what that means is every hemoglobin molecule at the muscles would look a bit like this. It's let go of 1 oxygen and it's held on to 3. And that's just because you can think of hemoglobin as like a good Samaritan. So let's say that's the muscle and then that's the capillary. When hemoglobin arrives at the muscle, it notices that there's not as much oxygen at the muscle. The muscles need oxygen. So hemoglobin is like, well, I've got plenty of oxygen. I'll let go of 1 and you can have it. So the important concept to note here is that when oxygen is bound to hemoglobin, like these 3, it's stuck in the blood. It can't diffuse out into the muscle. Whereas once hemoglobin has dissociated with oxygen, that oxygen then becomes available to diffuse into the muscle. And that's what we're going to talk about. Like the relevance of the Bohr shift is pretty much just saying that during exercise, hemoglobin dissociates even more than normal. And that just means that there's even more oxygen available to diffuse into the muscle. That's what we're going to get on to talking about. But for now, what this graph is showing us is that when there's loads of oxygen somewhere, hemoglobin isn't letting go of any. It's not dissociating with any oxygen. However, when there's not as much oxygen somewhere, like at the muscles, hemoglobin is dissociating with more oxygen to provide the muscles with it. Now, the important thing that they're going to ask you about is, well, what does the Bohr shift show? And I think some students get a bit lost with this, thinking that there's a Bohr shift that happens in the body. There isn't. It's purely just an illustration on a graph. But the Bohr shift is when the oxyhemoglobin dissociation curve shifts to the right, and you would always get a mark for putting that. Even though it's just this hypothetical thing that you draw on a graph, you always get a mark for mentioning that. So the oxyhemoglobin dissociation curve shifts to the right. And if we now work up to the Bohr shift line, from that same point, if we're working up to the Bohr shift line now, instead of hemoglobin being 75% saturated with oxygen, the Bohr shift line is showing us that hemoglobin is now only 25% saturated with oxygen. And what that's showing us is that instead of hemoglobin only letting go of 1 oxygen, hemoglobin is now letting go of 3 oxygens. Now, you don't need to state the amount of oxygens. This is purely me just using 1 hemoglobin as an example, so you can sort of make sense of this y-axis. But ultimately, the important thing that they want you to say in the exam is that the Bohr shift shows that there is an increase in the amount of dissociation going on. Hemoglobin is letting go of even more oxygen than it usually would do. And the Bohr shift happens during exercise. So what this is saying is that as a result of the Bohr shift, it's showing us that during exercise, hemoglobin is letting go, dissociating even more so than it was at rest. And the reason why that is so important is that if I just go to this diagram here, let's say instead of hemoglobin just letting go of 1 oxygen, each hemoglobin, as a result of the Bohr shift, each hemoglobin is now letting go of 3 oxygens. So there's way more oxygen now dissociating. And all of that oxygen is now available to diffuse into the muscle. Because remember, when oxygen is bound to hemoglobin, it cannot diffuse out of the blood. Hemoglobin has to dissociate with that oxygen first so that it can then diffuse out of the blood and into the muscle. And that's why the Bohr shift is so beneficial during exercise, because what the Bohr shift is showing us is that during exercise at the muscle, hemoglobin is letting go, it's dissociating with even more oxygen. That means even more oxygen is available to diffuse into the muscle. And the reason why that's such a good thing is it means that eventually the muscle has even more oxygen diffusing into it, and that can then prolong the use of the aerobic system. It can delay OBLA and delay lactic acid production. So that's the relevance of the Bohr shift. Ultimately, it just means that hemoglobin is dissociating with even more oxygen, making more oxygen diffuse into the muscle and delay OBLA. Now let's talk about why the Bohr shift happens and what they would want you to put in the exam. So in terms of the reasons behind it, we've said that it's this shift to the right. So you'd always get a mark for saying that the Bohr shift is when the oxyhemoglobin dissociation curve shifts to the right. You'd get a mark for saying why does it occur, and it's due to an increase in any of these three. So either an increase in CO2, lactic acid, or body temperature. You'll normally always get a mark for stating one of those three. I'd always put all three, but normally they're all under the same mark point. And as a result of those things increasing, what this does is it lowers hemoglobin's affinity for oxygen. And affinity is just a fancy term for attraction. So if I said that hemoglobin has a high affinity for oxygen, it means that it has a really strong attraction to it. Whereas if I say that hemoglobin's affinity for oxygen has gone down, that means it has less of a strong attraction for oxygen. And that means it's easier for hemoglobin to let go of that oxygen. And that's what's happening. So as a result of these things increasing during exercise, so let's pick one of them. Let's just say body temperature. As a result of an increase in body temperature, that lowers hemoglobin's affinity for oxygen. So hemoglobin's affinity for oxygen goes down, its attraction for oxygen goes down, and as a result of that, as a result of the affinity going down, that means that then more dissociation can happen. So you can almost think of it as like during exercise, as a result of an increase in temperature, hemoglobin becomes less, almost like, think of hemoglobin as a magnet. It becomes less of a strong magnet for oxygen, and therefore it's got a weaker attraction, a weaker affinity, and therefore it can dissociate with more of it. So they're the key things that they'd want you to mention if you get a question on the Bohr shift. Stating that it's when the oxyhemoglobin dissociation curve shifts to the right, 1 mark. As a result of an increase in body temperature, let's say, 2nd mark. As a result of that, that lowers hemoglobin's affinity for oxygen, and that then increases the amount of oxygen that is dissociating from hemoglobin. And then as a final point, why is that good? It means that more oxygen is available, that is in bold, to diffuse, that is in bold, into the muscle. That is in bold. So to get that 1 mark, there are 3 terms that need to be there. So you're saying that as a result of hemoglobin dissociating with more oxygen is available to diffuse into the muscle. That is the final mark. And then if they say, and then why is this good for performance? You then go on to say, this means the muscle can respire aerobically for longer, delaying lactic acid. So that is the Bohr shift and the oxyhemoglobin dissociation curve. For OCR, I have seen a question where they ask about what happens to the Bohr shift during recovery instead. And it is literally just the opposite of what we've said. So during recovery, you would say that the oxyhemoglobin dissociation curve shifts back to the left. That is because of a reduction in body temperature that increases hemoglobin's affinity. It becomes strong. It has a stronger attraction for oxygen again, and that means that it would be dissociating with less oxygen in recovery. And if you think about it, that makes sense, because in recovery, the muscles don't need as much oxygen anymore. So you can almost think of hemoglobin noticing that the muscles' demand for oxygen has gone down, and therefore it's just not going to give off as much of it as it was during exercise. But I would say 9 times out of 10, they're going to ask you about the Bohr shift shifting to the right rather than the opposite of it going to the left. And then the final thing to note here is sometimes they're not going to, I'd say for AQA, normally they just say, like, describe the Bohr shift. They're quite direct. But with OCR, they're less direct. Sometimes what they might just say is outline the process of gas exchange at the muscle during exercise. So if we write out the key terms there, if you get a question that is to do with gas exchange at the muscle and during exercise, those 3 things, if it's a gas exchange gas exchange question at the muscles, not the lungs, during exercise, that is your hint to talk about the Bohr shift in your answer. It's not going to be your whole answer, but there is definitely going to be credit in the mark scheme for you mentioning the Bohr shift. And let's explain why. Gas exchange is this is part of gas exchange, but on the specs, gas exchange is its own topic. But just to briefly touch on it here, let's say this is at rest, and these dots are just gases. At rest, the diffusion gradient might look like that. But during exercise, the diffusion gradients always get way steeper. And you can use the Bohr shift to help explain why the diffusion gradient gets steeper during exercise at the muscle. So what happens is during exercise, there'll be an even higher partial pressure of oxygen in the capillary, and there'll be an even lower partial pressure of oxygen in the muscle. But to explain why there's that even higher partial pressure of oxygen in the capillary, you can mention the Bohr shift. So you could say, as a result of the Bohr shift happening during exercise, hemoglobin is dissociating with even more oxygen. And that means that even more oxygen is available to diffuse into the muscle, helping to create this even higher partial pressure of oxygen in the capillary. So just be aware, for OCR students, sometimes they're not as direct as AQA in asking about the Bohr shift. So if you do get a gas exchange at the muscle during exercise question, throw in your knowledge about the Bohr shift. So let's have a look firstly with AQA, how they ask about this. So here it says the figure below shows the oxyhemoglobin dissociation curve. During a 400-meter hurdles race, the curve shifts to the right. Explain the causes of this change to the curve and the effect that it has on oxygen delivery to the muscle. So if we quickly scroll down to the mark scheme there, so question 25. So you can see here you get a load of marks. I wouldn't bank on these being separate in every mark scheme, but why does it occur? That's what it asked in the question. Due to an increase in body temperature, an increase in CO2, or an increase in lactic acid. It's known as the Bohr shift. And what does it result in? It means that as a result of these things changing, hemoglobin's affinity for oxygen goes down, and that means that hemoglobin is dissociating with even more oxygen. So you can see all those points there are in the mark scheme. Now, if we go to an OCR question, We'll skip. I don't really like this question because actually I think you should mention the dissociation of oxyhemoglobin first to then explain the change in the pressure gradient, like we were talking about here. But instead they've gone the other way around. It was a 6-marker split into 2 3-markers. So it asks you to assess how changes in the pressure gradient and the dissociation of oxyhemoglobin affect oxygen diffusion at the working muscle. So let's just go straight to this bit. Assume it's a 3-marker. Let's say they're asking you to assess the changes in the dissociation of oxyhemoglobin during exercise. So let's have a look at the mark scheme there. So you get 1 mark for acknowledging the Bohr shift, and that it's when the oxyhemoglobin dissociation curve shifts to the right. It happens due to an increase in CO2, lactic acid, or body temperature. This results in hemoglobin's affinity for oxygen decreasing, and that because hemoglobin is now not having as strong an attraction for oxygen, that causes an increase in dissociation between oxygen and hemoglobin. And as a result, more oxygen is available to diffuse into the muscle. And that's what we were talking about there earlier on. So that's the Bohr shift and the oxyhemoglobin dissociation curve topic all done. I hope you found that useful. Let me know in the comments of any other topics that you'd find useful for me to break down. And as I say, as I've said in previous videos, I do offer one-to-one online tutoring, helping you break down topics, apply it to exam questions. I also help with coursework elements like the EAPI and the written coursework for AQA as well. So feel free to click on the link in my description and it will take you to my website.